All right. Hello, everyone. Thanks for joining us for this NPS Automotive webinar. Now, today's session addresses a very common question that we get from customers, namely, how can I ensure that a given automotive product qualification meets my application mission profile? And how exactly do the two relate? So today we're going to have our European senior customer quality expert, Thomas Eichenberg, share his keen insight into this topic. All of our webinars are available for on-demand streaming at monolithicpower.com/webinars. We'll of course be adding today's session in a day or two, so please expect a follow-up email with details. Now, finally, all attendees are on mute for the webinar, so we ask that you submit any questions. You'll see a Q&A button in your Zoom application menu. We'll cover all of these at the end of the webinar. Now, Thomas, over to you.
Thank you, Alan. Thanks for the introduction. This is Thomas speaking. With that, I suggest we go straight into the topic, and let me introduce the agenda for the next 15, maybe 20 minutes. It might be a very long agenda for this short period of time. Just wanted to highlight a couple of keywords that you have a good understanding what you can expect, what will be talked about. So first of all, we want to look at what is a mission profile anyway, where does it come from, how is that used, what is the background? And then we want to look a little bit into what means stress to silicon and what means stress to an silicon device, to an IC device. And relative to that, how is that qualified during the original device qualification? And then we want to see how an assessment should be done, whether or not an existing or qualified component can be used in a target application. We will look into fail mechanisms and how to model them. And we will understand what an acceleration factor is. And derived from that, we will understand what is an equivalent qualification stress and how we calculate that finally in a real life example. And as Alan said, at the very end, we will have a Q&A session. I will be open for questions at the very end of this session. Now, what is a mission profile? What you see here on the right-hand side table, this is a very typical mission profile, how it is expressed. And this relates to lifetime of the application in the field. Here in this specific sample, it's 15 years lifetime. And you see this mission profile is split into active hours and passive hours. That means the device is active in operation for that period of times listed here and is non-operational for this period of times here. At the same time, you see the temperatures are mentioned in junction temperatures. So the differentiation between active and passive is not really meaningful, because by the end of the day, you always want to make sure you calculate these junction temperatures, which is the temperature, excuse me, of the silicon itself, not the ambient temperature. If you have an ambient temperature available and you run a power device that has significant self-heating, you need to take into account that the junction temperature is or can be significantly higher than the ambient. And with these period of times listed here, you try to mimic the stress that the device will be seeing in the field over the entire lifetime. Okay. And this stress, what is listed here is mimicked in the qualification, in the original qualification of a device, by the so-called HTOL testing, high temperature operating life test. And we come to that details a little later on. There is other mission profiles that relates to other stresses in the field, and I think the next one that is widely used is on temp cycling to mimic thermomechanical stress. And you express this here by delta temperatures and also how many temperature variations this device will see in the field. That means with the temperature cycling, you can mimic thermomechanical stress that is being applied to the application and all the components in the application. And with the HTOL stress test or qualification test, you can mimic voltage and temperature impact and aging effects to the not only to the silicon, but also to the package and the whole component. And probably other stresses are out there and can be mimicked, but these are the most common ones are used when it comes to emission profiles and to estimate whether or not a device is okay to handle all that anticipated stress or not. And that means, or given that with this stress, the device performance will degrade slowly over time. Okay. Will it, by the end of the lifetime, still be able to meet the datasheet specification or whatever was specified on this device? This is the estimate, the decision that needs to be made. I want to mention here that numerous qualification tests are out there. I mentioned temp cycling and HTOL here already. And all these stress tests that are available are mainly defined by the JEDEC organization and by the AEC organization when it comes to automotive. Here, this is just an excerpt of the AEC Q100 standard, qualification standard. And on the left hand, you just see the front page of this standard. And then on the right hand, you see in the left hand column, all the stress tests listed that should be applied during a qualification for automotive. And here, this red one is just zoom in and you can see here is the HTOL listed, as well as the storage life, which is the non-power equivalent of the high temperature operating life test. And here you see it's a JEDEC standard with a JES-D number to it. This is where all the conditions are defined, how such a stress test need to be run. Here's another excerpt of the AEC Q100 standard. And just wanted to highlight the flow, mainly here on the left-hand side, just very briefly, who actually can do such a mission profile calculation or should do it from the AEC Q100 point of view. And you see here, this decision point here, it says basic calculation. So this entire left-hand flow should be done by the tier 1. So typically the party that buys ICs to put them into their application, which will later be used in a car. So the tier 1 needs to make a decision or needs to find out, has a basic calculation been done? And the basic calculation means nothing else but has the qualification been done, especially for mission profiles, the HTOL test. If the answer is yes, then the tier 1 has basically all the information on hand that they can use to make a calculation if a certain mission profile is kind of overstressing or understressing a given device. Let's go more into scientific approach right here and go into details how a calculation is done. This is another excerpt of the AEC Q100. And you see just 2 lines in here. The one is the operation, and this refers to HTOL testing. And the other is thermomechanical stress, and this refers to temp cycling stress, qualification stress test. Let's look at the first line over here, which is targeted to mimic the stress to the device in operation at high temperatures. Here in specific at 125 test temperature or 87 degrees C use temperature. Okay. What you see over here is actually a mission profile. It has only, if you will, one data point, 12,000 hours lifetime at 87 degrees C. Okay. Over here, this equation here is also known as the Arrhenius equation or the Arrhenius model. And Mr. Arrhenius at that time, more than 100 years ago, maybe 150 years ago, invented or found out how material can age over time, and how that happens is expressed with this formula here. The formula is relatively simple, given the fact that there is widely constants in there. This over here, the EA, is the so-called activation energy. It's 0.7 electron volts for CMOS technology in ICs. And there's other activations energies out there depending on the technology. Down here is the Boltzmann constant. And then you need to enter your use temperature down here and your test temperature down here. And what you get with this formula is the acceleration factor. That means how many hours in stress test conditions will be equal to the time in the field. Okay. And with this acceleration factor, you can go into this formula over here, which translates the time of usage relative to the time of test. Here in this specific example, you would need about 1,400 hours at 120 degrees C to represent exactly the same stress as 12,000 hours at 187 degrees C. Okay. In the AC Q100, the qualifications shall be run only at 1,000 hours. This is just more or less an arbitrary set point, where at this point in time, the AC committee said this is fair enough to estimate the reliability of an IC. Down here, for the thermomechanical stress, it's exactly the same approach. You have the mission profile input here, and then you have a model. And this one was invented by Mr. Coffin and Mr. Manson at that time. They came up with this formula here. Again, you calculate an acceleration factor. You put it into similar formulas here, and you end up in a representative stress. In this case, about 1,000 cycles at this temperature delta, 76 C. And again, the IEC Q100 defines 1,000 cycles to be done. Okay. Now, if you have a mission profile, you want to understand what is the equivalent stress that this mission profile is presenting. And then you want to understand, is this equivalent stress more or less than the original qualification stress? If this stress is higher than the qualification stress, then there is some risk, if you will, that the parts will fail prematurely relative to the application life. And if the equivalent stress is lower, then you're pretty much on the safe side, and you can say the parts will not die just from aging effects before the end of the application life. And that takes us to the real life example already. So we look at this table that we have seen before, this mission profile. And here is the Arrhenius model, just to give everybody a reference. And what we do now is we look at the first pair of data, which is minus 40 C junction temperature and 45 hours of duration being in that temperature point. And we enter this temperature into the Arrhenius model over here. Please be noted, you need to calculate in Kelvin, not in Celsius. So you enter the 125, your test temperature, and you enter the -40 into here as your real life temperature for that data point, and you calculate a relatively high acceleration factor. If you use this formula as we have seen before, and you do the math, you enter the 45 hours over here into the usage time, if you will, then the test time that is needed to represent the stress of this pair of data here is a very small fraction of an hour. Now, you need to continue to do these steps, exactly what we have done here, for all the data pairs that are given in the mission profile, and accumulate all the fractions of test times that you have. And if you do that for this particular example, you end up in almost 6,000 hours of HTOL testing, which is your equivalent qualification stress for this mission profile. Now, our standard definition of AEC Q100 HTOL testing says, oops, you need to do 1,000 hours only. And that is what most people do in semiconductors. But with this example here, you would say, well, my real life stress is 6 times higher than the qualification stress, which is meaning probably there's a high risk that the devices may fail earlier than my application end of life. Now, how can we overcome this problem here? So the first thing is you may want to reduce the stress in the field, the stress to the application. And this can be done by just lowering the junction temperature. And lowering the junction temperature means either you bring down the ambient temperature, which is maybe not possible, or you cool the device by proper heat sinking, air circulation whatsoever. If that is also not possible, then you may want to try to extend your qualification and see how far can I take my device really before I will start see failures in HTOL testing. So you can take up your junction temperature during HTOL testing maybe to a 150 C. And if you do that and do the math again that we have just done in the previous slide, you would end up in an equivalent stress of only 1,700 hours rather than almost 6,000 hours of stress testing. If you have not seen failures in this 1,700 hours, then your level of confidence has certainly increased that the device will be able to take all the stress, but still, the equivalent stress is higher than the actual qualification stress. The next step would be to increase the test time, because you cannot take the devices, the silicon, higher than 150, as this is the absolute max temperature that a piece of silicon can take without any risk to damage it just because of the temperature. And if you would do the same calculation with 150 C for 2,000 hours, you will be safe at the end. Your level of confidence is very high that the device can survive the target application stress over the entire lifetime, and not only survive, but maintain the defined and specified performance. And with that, I'm already done with the presentation. With that, I say thank you for your interest, and I open this for the Q&A now.
Thanks very much, Thomas. So folks, if you have any questions, please go ahead. You can submit these through the Q&A menu option that you guys will find inside of your Zoom menu. And we'll wait, let's say 30 seconds or so to see if there's any questions coming through. And yes, folks, if you have questions, yes, please type them in through the chat feature. All right, first question is, do we only guarantee up to 15 years on our devices?
No. So these 15 years that we have talked about is just one example of a specific mission profile. What we warrant is covered in actually our qualification report, if you will, and the standard qualification would represent exactly what AEC Q100 defines relative to HTOL, which is the, I think, 12,000 hours at 87 degrees C junction temperature. And whatever that means, 12,000 hours operation, whatever that means in real life is dependent of the use case of the application, of course.
All right, next question is, can we put these calculations, in an Excel file? Let's say you're given a specific EA.
Yes, I think the question is more, can we make the calculation easy by using Excel macros? And yes, definitely. So if you know how to use Visual Basic, you can program an Excel sheet that would allow you to do, I don't know, a table with temperature points and duration points, and then just click a button and the Excel does all the math for you and comes up with the equivalent stress, and then you can compare it. Is this higher or lower than the qualification stress? It takes a little programming skills, but it's definitely doable.
All right, next question. Let's see. Do we monitor different intervals of the temperature cycling? So let's say TC 100 or 500 or 1,000, and consider any failures that happen in between.
The condition is, if you want to pass this test, the condition is all devices must pass. If there is a failure at a given point in time or after a certain number of cycles, you need to investigate, is this failure because of the test cycling, temperature cycling test, or is that a failure because of, for instance, mishandling the device, like a bent lead, or disconnected to the socket or whatsoever? And if it is related to test temperature cycling stress, then obviously the test is a fail, and you need to figure out how to make the device more robust so all devices can survive the test.
Yeah, and just to add to that answer, it's pretty common that when we qualify a device, we will have checkpoints in between, not just for temperature cycling, but for things like HTOL, and just make sure that the part still is looking good, because you don't necessarily want to wait until the very end to have an early look ahead. All right, next question. From your experience, how much calculated lifetime values correspond to real values? So how much do the calculated lifetime values correspond or correlate to our real values? How precise is this model? And is there any kind of acceptable deviation?
So this model, the Arrhenius model, is the industry standard. I think everybody, at least in the semiconductors, refers to it. How accurate that really is, I can't answer this to this precision. But to answer this maybe in this way, the mission profiles, that is the most, the biggest factor that is hard to really calculate and translate into real life. There's many different mission profiles out there for, I don't know, truck applications versus passenger car applications versus whatsoever. And these mission profiles always try to be as close to real life as possible. But this can be only a good estimate. And this is probably the parameter that would cause you the biggest mistake in all the calculation. And then, you know, it can happen that your calculations say, well, 1,000 hours is the equivalent stress, and you have tested 1,000 hours, so I'm good, definitely. Very likely, yes. However, if the answer is, I have calculated 1,100 hours versus 1,000 hours qualified, that does not mean the devices will fail, you know, over 1,000 hours. This just means, well, our stress is a little higher than the device was qualified to, but the qualification only looks at 1,000 hours. We have not looked at 1,100 hours. And very, very likely, the devices will survive the 1,100 hours or even much more.
I think, in fact, this is a good segue into the other question that we have here, which is, should testing until failure be done to correlate Mech model predictions?
Yeah, testing to failure is requested often, especially in the automotive industry. And some people try to understand what is the so-called robustness margin. And Alan, you're right, this is a perfect add-on question. During the standard AEC qualification, you only look at, you know, the example HTOL up to 1,000 hours or maybe 2,000 hours, but you still don't know for how long these devices are really able to survive or keep up the specified component. On the other side, running those tests, you know, to failure, especially for HTOL, for others it might be easier. It takes a long time. And with that, also a lot of money. And it's always a kind of a trade-off. How much money do I want to spend on how much more accuracy to gain? And in my 20 years plus semiconductors quality life, I have never seen a reject coming back just because of aging effects. That can have various causes, of course, but I believe it just needs a good estimation. Is my mission profile, is my expected field stress exceeding the qualification dramatically, or are we close? And then you need to do some sort of a risk assessment. You know, is my level of confidence high enough? If not, then you may want to ask the IC maker to extend the qualification just to gain your level of confidence.
All right, Thomas. Next question. How do we differentiate between life models and temperature durability testing and thermal cycling?
Oh, can you repeat the question? I believe it's a difficult question.
Basically, you know, in the qualification process, there's a lot of temperature cycling done and testing at extreme cold, hot temperatures and all this. And so I guess in general, how do we differentiate between just looking for the capability to handle the temperature cycle itself, maybe thermal shock, versus, you know, what's being covered to look for this this mission profile modeling? You know, so how do we differentiate basically between, you know, what you're testing for the mission profile, for the temperature durability, and thermal cycling, or maybe thermal shock? Or are you really still looking at perhaps all three in concert, you know, at the same time?
Oh yeah, so all these stress tests are designed to provoke certain failure mechanisms, right? So voltage in semiconductors can cause different aging effects than thermomechanical stress to the device. And temp cycling is mimicking other failure mechanisms than thermal shock or latch up or ESD. All these kind of stress tests are designed to provoke certain failure mechanisms. And all these tests, we have seen all the lists there of AEC Q100 stress tests to be made. These all together should provide a level of confidence that the device will not fail because of these stresses, these sorts of stresses being applied in the field. So there is, I think, meanwhile 70 years or 80 years of experience, what sort of stress is out there and how can it be mimicked. And these stress tests are I believe, are very close to real life. The art is just to differentiate all this. What we talked about is device level stress testing. If you put that onto a board, into an application, you also would need to run application and system level qualifications, as there is different failure mechanisms appearing as just on a device level.
All right, folks. So that was the last question. I'd like to thank you all again for your participation today. And of course, thank you to our European Senior Customer Quality Expert, Thomas Eichenberg, for the insightful presentation. Expect an email, everyone, from us with a link to view this offline at your leisure. And thanks for joining us, and we'll see you for the next one very soon. Take care.